Hello, today we're going to talk about thermodynamic and kinetic control. Okay, so we need to compare whether or not a reaction will occur without outside work versus the activation energy. Okay, so if you remember when we were looking at energy profile diagrams, you'll typically see a reaction like this. Okay. This time I want to draw a reaction profile diagram specifically with delta G in mind. So this is the free energy. Okay, over the course of the reaction. Now, the energy difference between the reactants and the top of the hill, or the highest energy state, that is the activation energy. And then your products are down here, and the difference between your reactants and your products will be your net free energy change for this particular reaction. So this one will be thermodynamically favorable because delta G is negative. It's going down from the reactants to the products. So it's releasing free energy. It's favorable. But it has that activation energy hump. Any reaction has to meet that activation energy, the minimum energy required for the reaction to start. So when we say it has thermodynamic control, you want delta G to be negative thermodynamically. Thermodynamic control. If delta G was positive, then it would be not thermodynamically favorable. Now your activation energy, that is based on the kinetics of the reaction. It depends on the collisions and the energy of those collisions. You should go back to Unit 5 if you're not sure about some of those kinetics things and kind of review Unit 5. So you can have a reaction that has a negative delta G, that has thermodynamic favorability, but it still doesn't happen. And the reason it doesn't happen is if it doesn't have enough energy to get over the hump, to exceed the activation energy barrier. And so if it doesn't have enough activation energy, we call that kinetic control for the reaction. Just to make sure, or to compare rather, I'm going to draw the other type. If it starts low and high, the activation energy is still between the reactants and the top of the hump, the activation energy barrier. But the difference between the reactants and the products is the delta G, and as long as this is free energy, and they will specify, this delta G is positive, so that is not thermodynamically favorable. Let's look at a few examples. We have this reaction. 2AB2 is yielding 1A2 and 2B2. The sign for delta S, you're going from 2 particles to 3 particles. That's getting more disordered. Delta H, they told us it was an exothermic reaction, so delta H must be negative. So delta G will be negative always, because it is positive for delta S and negative for delta H. Both of those things are thermodynamically favorable, leading to delta G always being thermodynamically favorable. Now, this reaction does not proceed at room temperature. Can you suggest a change to the conditions that makes the reaction proceed? It does not proceed at room temperature because the activation energy is too high. So a change to the conditions that makes the reaction proceed, you could increase the temperature, make the particles move faster and collide with more energy, or you could use a catalyst to lower the activation energy barrier. Okay, so now this is the reverse reaction of the previous example. You're going from 3 particles down to 2, so delta S is negative. We had an exothermic reaction before, so when we reverse the reaction, this one will be endothermic. And so delta G will be negative never, because both of these things are not favorable. Now it says the reaction does not proceed at room temperature. Can you suggest a change to the conditions that make the reaction proceed? No, I can't. Because it is never going to happen spontaneously at room temperature because of the values for delta S and delta H. It will never work. Okay, here's another example with iron and oxygen reacting to form iron 3 oxide. So they give us delta H is negative, it's exothermic, delta S is negative, it is decreasing the amount of disorder. If you calculate delta G, you would do delta H, which is the negative 1648, minus the temperature, which is 298, times negative 0.544. Make sure you change that to kilojoules. You get that the delta G is negative 1486, so it is thermodynamically favorable at that temperature, but it proceeds very slow because it has a lower activation energy. When you add water, it becomes faster, and that's probably because it is increasing the amount of successful collisions when you dissolve the products together. And then what happens to the value of delta G when the water is added? There will not be any change. When you add a catalyst or anything that's just changing the number of collisions, it does not affect the amount of free energy associated with the process.